Okay, good. So now that your opinion was corrected, now I can start teaching very badly. Okay. I'm not saying that I taught well so far, but now I can worsen, let's say. Okay, so here we are. I assume and I hope that everybody of you has the data available. And let's now try to compute the density. So, what we have to do is, first of all, to decide what is the interval, the time step delta x. And I suggest that given that this time series, the minimum is about, let's see, should be about 600. No, it's, okay, let's start from 0, and the max is almost 10,000. So I suggest that we use a step of 100, which means that in the first step, 0, 100, we will get no data. In the second step, we will get some, etc. In this way, we adopt about 100 steps, which is fine, I mean. And of course, we could also reduce delta x to 50, but it becomes more computationally expensive. So my suggestion is, first of all, let's start with 100. And the way in which we can count the number of data in a time series that are included in a certain interval is this. We can, just me show you how we can do it, and then we need to do it iteratively. Let's let's refer to the first time, to the first step. So it's length for river, and if I just close with it, it's the total length. And now I have to tell R to refer only to a given interval of river flows. So if I well remember, we can make it in this way, for river greater than 0. And I think let's try in this way. I don't remember well how to put two conditions, but I think this is fine. And for river less than 100. So if we do this, we should get 0 if it is correct. Fine. Let's now try with from 100 to 200, and we should get some. No, it's still 0. So let me check whether, yeah. So only one commercial E. So you see this is the correct. It's 0 between 0 and 100. It's 0 between 100 and 200 is 8, etc. This is the way in which we can compute the number n, which refers to a given interval. Okay. Now we have to compute this several times for each of the intervals. So I suggest a fourth cycle. And the fourth cycle should be between 1 and 100, because the number of intervals is 100. So I suggest that we open a text editor in order to write the instructions on the text editor first, and then we can copy it in R. So let me open a text editor, and please open a text editor of your preference. If you're using RStudio, you already have it. So let me open this text editor. Okay, you can use this. So let me try to write for, it's large enough, not really. Let me see, tools. What is the font size? Just 1 second. The preferences. Okay, now it's visible. For I in 100, and then let me open a curly bracket, a left curly bracket. before we open the for cycle, let me define the vector that will collect the series of the lowercase n's. So I can write n vector equal, repeat, 0, 100. In this way, I created a vector which is called n vector, which counts 100 zeros. Now I can write n vector I is equal to length or even. And now I have to put the range, which should be varying with I. So I suggest that we use this, I minus 1 times 100 and, or even less. And or even greater, not less, and or even less of I times 100. It should work in this way. Can you read it? Yes. It should work in this way because, let's try to reason on it, to make some reasoning on it. When I start with the first I, which is 1, I get for even greater than 1 minus 1, 0, times 100 is 0. So for even greater than 0, and for even less than 100, because I is 1. When I turn to the next step, I is 2. And so I will get for even greater than 100, and for even less than 200, which is fine. Okay? Really, that is to say that we run a very small risk of missing some values, because if we have values that are strictly equal to hundreds, multiples of hundreds, we miss them. But it is quite unlikely. In order to avoid this, we should put a less or equal somewhere, but I think we can discard it, because the approximation is very small. By the way, I think less or equal, it could be done by, I think in this way. We may try it, okay? Okay, perfect, and I think that now we can close the for. Should work.
I think we miss a bracket.
Yeah, maybe, sorry. Let me see. Yeah, correct, here. I missed the bracket here. Good. And now, in order to get the density, I have to divide n vector is equal to n vector divided by length or even divided by 100. This is what is written there. And we should be all set now. Let's see if it works. I make a cut and paste. Let me see. I make a cut and paste because it's a short program, so I can make a cut and paste. Let's see if it works. I clear the screen. Yeah, it seems yes. Let's see n vector. Let's see the values. It seems that it's working. Now let's try to plot it. So, clear the screen, plot, n vector. And n vector should be if we wanna, we need to build the abscissa. And the abscissa should be the same length than n vector, so it's 100, and should be 0, 100, 200, 300, etc. So I think that we may write in this way, n vector x is equal to sequence 0, probably it's, okay, let me see, 0, 10,000, and the step is 100. Let me see what is the length, because I think I put one too many. No, it's fine. Okay, let's see if it works. Ah, no, sorry, n vector x. Yeah, 101. It's not good. So, actually, let's do like this. Now the length should be fine. Okay, perfect. What I did basically, I built the abscissa in this way. Actually, the abscissa is constituted by steps, and if I wanted to be very precise, very strict and rigorous, I should use for each of these steps, the first one is varying from 0 to 100, I should build the abscissa in the middle. But, you know, we are just performing an approximate estimation. So what I did is to put the abscissa on the left of each interval. So I started from 0. And I went up to 9900. Is this clear, what I did? Because I want the graph starting from 0. Okay, now let's see with the plot what happens. And remember that I am expecting something that is long tail on the left. Plot and vector x type equal line. I inverted the x with the y, so let me go back, because first I have to put the x. The plot instruction wants the abscissa first. And you see that what I got is indeed what I was expecting. It's a perfect probability density with the long tail on the right, which says that the maximum density is about around 1000. Do you remember what we said yesterday? Meaning, the integral of the probabilities should be 1. So let's try if the integral times delta x. Let's try to compute the summation. So let's do this. Sum n vector times 100. And let's see if it is 1. 1. Perfect. If you understand what we are doing now, you perfectly understand the theory that we made yesterday. And you perfectly understand what the probability density is. So yesterday, the discussion was a bit complicated. You may remember, maybe that it was also a bit too quick. But again, if you understand what I did with this code, if you understand this, it's very simple, just a few instructions. If you understand this, then you understand what I did yesterday. I'm just counting the number of occurrences in each small interval. By the way, we had a quicker way to compute the density now. If we do this, plot density forever, type equal line, and let's look at the graphic window. This is maybe even nicer. It's not the same graph as before. This has been just computed with R. And what we could do is to superimpose the previous one on this in order to make a comparison. So let me do that. Lines are, let me go back to the previous instruction. Lines, and instead of type equal line, let's put line width equal 3. It's a bit thicker, I make the line a bit thicker, and col equal red. Here it is. You see that they are more or less superimposed. There are small differences. And in particular, you see that the black line is smoother. White is smoother because R, after computing the density, first of all, R uses 50 intervals by default. We use the 100. With the red line, we use 100 intervals. R uses 50. So you would expect that the figure by R is less smooth. But R, after computing the density, smoothes the results because it assumes that the density should be a smooth line without, short range variations, and therefore it smoothes it. And this is why it looks smoother. In order to get a better picture, let me invert the two. It's clearer. So this is, sorry, I forgot. This is our computation, and let me superimpose the other one. Okay, let's see. Now it's a bit clearer because the black line is above. So, again, you see that it's smoother, but it's nice to see that they are more or less the same, they are more or less equivalent. So our computation was indeed correct. Okay, now let's move forward with the annual maxima. Any question on this? Okay, the annual maxima. So first of all, we need to pick up the maximum, the annual maximum. And I think the easiest way is to put the data into a matrix. So let me do that. And for_1 equal array for_. Okay, let me do like this. Instead of putting the data into an array, let me write a for cycle directly on the time series. I think it is easier. So let me write it here. This is the text file that I used before, and let's define a vector of annual maxima. I fill it with the 90 zeros, and then let's make a for cycle from 1 to 90, and then let's say that max I is equal to max for_, and again I minus 1 times 365 I times 365. It should work in this way. it should work. Let's see, I cut and paste it. Let me see what is the problem here. Max I minus 1 I. Yeah, there is something which doesn't work here. Let me see what is the result. Okay, let me go back here because I need to see what's wrong. And max I. Okay, first let me do like this. I need to test it, so let me see what happens. 10. I think the reason may be that we need to put, let's try in this way. I think the reason is that, I go back to the program, sorry. I think the reason may be that we need to put a second parenthesis here. Let me see if this is the reason. Yes, it works now. So basically I needed to put a second parenthesis because otherwise it gets mixed up. Okay, let's see a plot of the annual maximum. Plot and max. Just for, you know, it's better to check that everything is working. It seems that it is fine. They are varying from 2,000 to 10,000. Okay, good. Okay, now what I should do is to compute. Now I have the series of the annual maxima. This is the series that I have to fit with the Gamble distribution. And you may remember that to estimate the parameters of the Gamble distribution, we need first to compute the mean and the standard deviation of the annual maxima. So let's compute it. So what I would like is mean and max mean, a bit complicated, but mean and max, and max SD equal SD and max. Okay, let's see what is the result for the mean is 5,000 and the result for the standard deviation is 1,700. Okay, good. Now we need to compute mi and beta. Let's go to my website and to look for the relationship to compute mean and beta. Mi and beta. So, probability theory, and they are here. Just 1 second. Here they are. Just once a year they are. Okay, so first of all, the standard deviation SD is equal to, which we already computed, is equal to beta times pi divided by square root of 6. Now I want to compute beta, so beta is equal to standard deviation multiplied by square root of 6 divided by pi. This should be equal to, if I well remember, 1 divided by 1283. Let me see. So, 6 to the power of 0.5 divided by pi. Sorry. I think it is just pi. Okay, 0.77. If I make 1 divided by 1283. Yeah, okay. So let's take 0.7796, etc. 97. 0.7797. So it's beta is equal to 0.7797 SD. Okay, let's compute it. Beta is equal to 0.7797 times N max SD. So beta is this value here. Okay, good. So we have beta. Now, let's go back to now we need to refer to this relationship here. Let me write it. So EQ is equal to me plus so this is the relationship where everything is known but me. So let's compute me. Me is equal to EQ, which is the mean that we just computed, minus 0.5772 beta. Okay, let's compute it. Sorry, mu is equal to and max mu minus okay, let's see mu, it's this value. Perfect, so we have mu and beta. Good. Now we are able to compute the river flow with an assigned retro period, the peak flow with an assigned retro period. In order to do that, we have to use the Gambit distribution. I hope you can read here. I remember how to write it. Even if I don't remember, so it's fx is equal to e to the power of minus e to the power of minus minus mi divided by beta. I don't remember how to the explicit expression for q. I need to derive it. So let me take the two logarithms as I did yesterday. So basically I can write logarithm of t minus 1 divided by t. T is our random period, and this is equal to minus e minus q min mi divided by beta. I change the sign, and then logarithm of minus logarithm of t minus 1 divided by t. This is equal to minus q min mi divided by beta. And then I can go up here and write, I need to change the sign again, minus, minus. So q is equal to mi minus beta, which multiplies logarithm of t divided t minus 1. This should work. Let's, now we are ready to make the computation. One may wonder whether it is correct because, you know, I may have made a mistake. So the first thing to do is to make a kind of check. So now we apply this relationship without wondering too much whether it is correct or not. But let's make a check. And what is the check? The check, based on our understanding of what we are doing, may be the following. What is the length of the observation period of our time series? It is 90 years. And so what is the retro period of the maximum value that, an approximate retro period of the maximum value that we see during these 90 years? Okay, our guess would be that the retro period approximately should be 90 years. So let's try to apply this relationship here by using a retro period of 90 years and see whether the resulting Q, the resulting big flow, is close to the maximum observed value. Let's do that. So first of all, let's compute this. And let's say that, let's call it capital Q, is equal to mu minus beta times, I think it's, I don't remember if it is log in R or ln. Let me try with log. I think it is log. Minus beta times log, and let me try with, I said 90 years, so 90 divided by 89, and I need to close 1, 2 parentheses. So let's see what is Q here. It's 10,000, and the max of Fourier was, yeah, fine. There is a difference, of course. We are not expecting the same value, but it's reasonable. I mean, there shouldn't be very macroscopic errors. Okay, good. So you see that it's quite easy. Of course, we are still missing here a goodness of fit checking. I told you that we are not taking into consideration this. But what is required by our exercise is instead to compute something different. Let me see, I go back to the PDF. It says, a graph of the progress of the estimated peak flow for increasing retro period is also required. Okay, so let's compute the peak flow for retro period varying from 1 to 1000. Let's do that. So I think that given that we have to write a for cycle, let me go back to my text editor. And let me write, first of all, peak equal, or peak flow equal repetition of 0, 1000, and then for I in 1, 1000, curly bracket, and then let me go back to R and compute and take a copy of this. I go back to the program and let's see here, peak flow I is equal to, so here I have the retro period. The retro period, if we start from 1, there is a problem, because here there should be I, and here I minus 1. The problem is that if we start from 1, retro period of 1 year, we get a 0 at the denominator, which is a problem. So let me start from 2. So the first retro period, which we can compute, is 2 years. So the first element of the vector will be 0, no problem. And then I think we can close here, and we should be done. Let's see. Good. Now let's see what is peak flow 1. Should be 0. Perfect. And what about peak flow 2?